As the last topic of this course, we are going to talk about electromagnetic waves. This is a subject which is complicated, both mathematically and physically. So you're going to cover this in the third year in electromagnetism courses. But it's actually nice if we have a good idea about how these waves are structured. So as a result, we are going to say something about electromagnetic waves. Especially, I would like to show that these waves obey Maxwell's equations. But I'm going to do this in a separate video. In this video, I'm going to talk about, in general, the waveform. I'm also going to talk about the waveform of the electromagnetic waves at some point. The reason is that we haven't actually covered this waveform, the waves in general, in the previous semester. So as a result, it is necessary that we have to say something about it. So when I'm talking about waveform, the most common waveform that we meet in nature is the sinusoidal form. So as a result, I'm just going to draw this kind of a curve in here. This is basically a profile that depends on the position with this trigonometric sine or cosine function. Now, let me say a few things in here. Just compare this with the pulse form. A pulse is some kind of in a way, is a wave profile which is kind of present only in a restricted part of the space. Sometimes you have just a single peak, for example, for waves that are produced in tight ropes, for example. You might even have a single peak in there. But mathematically, these are complicated because defining the wavelengths and frequencies and things like that is a little bit complicated for these kind of waves. So as a result, mathematically, the sinusoidal waveform, the thing that we are going to do in here is going to be more suitable. So as a result, let's just erase this. So we are going to talk about this kind of a waveform. So in here, I'm also going to assume, that's an unphysical assumption, that this waveform somehow continues indefinitely in the whole space. So from minus infinity to plus infinity, this wave is present everywhere. So with this, of course, I can define the wavelength and the frequency and things like that precisely. And most of the time, this is what we assume. So just keep this in mind that this is for mathematical convenience. So we are also going to do the same thing for the electromagnetic waves. We are going to assume that these waves are present everywhere in space. But in any case, there are some properties of the waves. So I'm going to talk about the velocity, wave velocity. We will talk about the wavelength. So let me draw a wavelength in here. So from this point to that point is the lambda is the wavelength. And what else? There's also the frequency, of course, frequency. Or the period, or similar kinds of things that and numbers that are all related with each other that can describe a wave. So, important thing in here is this wave profile in here. So this displacement of whatever that is from this equilibrium position. So you might think that this is a water wave, and this is the normal profile of the water without the wave, and with the wave, of course, the surface of the water is displaced a little bit, or it might be a tightrope or whatever. So I'm going to call that displacement as u. So that displacement is a sinusoidal function of position. So let me just first write it down like that, and I'm going to add a few more things. But when I say sinusoidal, this can be a cosine function as well. There's not much difference between them. So if we write down the argument as some multiple of a constant k multiplied with x plus a phase in here, so phase should always be in there. This is essentially a function which is periodic in position. So x, as a variable of x, it's periodic. Okay, so as I said, there is no difference between sine and cosine. Whichever one I use, I can just change the phase in here and use the appropriate function in here. So I'm just going to use cosine in here for no particular reason actually. And then of course there's this wave amplitude in here, so that's the maximum displacement, so that has to multiply the cosine argument. So essentially what we have said in here is captured by that function in here. Right, so that's our function, but I'm going to change this function a little bit more. Let's just keep this in mind. I forgot to mention this. So this is basically the profile of the wave at a given instant in time. Let's say at time t equals t0. So only at that moment we have this profile. Now, what happens at a later time? So let's see. Suppose that we want to draw the wave profile at a time delta t later. So in this case, what you should keep in mind is that in these kind of sinusoidal waveforms, wave essentially as a whole is going to be translated uniformly with this given velocity. And that's why, I mean, this kind of a waveform is easy to work mathematically because of these kind of things. So as a result, we have the same shape, but this time the shape, the form, is shifted. How much is it shifted? It is shifted by a distance delta x, which is equal to v times delta t. Right? You can look at this shift from peak position to peak position, or from 0 to 0, or from that 0 to that 0, and so on. Let me erase everything in here. All right, just keep this in mind. So the next question is, how can I incorporate this into this functional form? The simplest way is this. I just write this thing down as k multiplied with not x but x minus vt. There's still a phase in here, probably. But that part is actually quite irrelevant. So you can see what happens in here. So for example, let's suppose that phase is 0. Forget about it. Forget about the phase. And suppose that, I mean, we are looking at this peak position in here. This particular one, right? So that position in here. So this is the position, whatever it is. So let's suppose that at that position, so that's x0, at time t equals 0, we have this x0 minus v times t0 is equal to 0. So the argument of the cosine is 0, so that the cosine is 1, so therefore we are at the peak position in here. Okay, so that means at a slightly later time, of course, the peak position would be slightly later position, right? But still the argument of the cosine should be equal to 0. So basically then, in this kind of a waveform, the places where the argument of the cosine is equal to 0 gives us this particular peak position in here. So let me just write them down like that. I don't know how to squeeze everything in here. So let me erase everything in here. So if the argument of the cosine is 0, for example, so these are basically our points which are moving with velocity v. So in that case, at these positions, the wave amplitude is equal to the maximum amplitude. The displacement is equal to the amplitude. In any case, we are in the peak position then. So what else? Of course, the argument, the whole argument might be equal to 2 pi, in which case, if that x minus vt is equal to 2 pi over k, then that's going to be, that's also a peak position. In that case, it is this peak position. If you want to talk about this peak position in here, in that case, the argument of the cosine would be 4 pi, and so as a result, we have 4 pi over k in here. So whatever. So as a result, these peak positions are basically moving with velocity t, because they have this kind of a position versus time relationship. So as a result, by doing this trick, I can simply incorporate both the position and the time dependence. Okay. So next thing is, how do I read the wavelength from here? So where is the wavelength in here? So let me just say it like this. I'm going to do one more change in here. So let's say that this displacement is, of course, a displacement at the position x and at time t, right? It's a function of both the position in space and the time. So basically the wavelength is this property that this u of xt is a periodic function of the position. That means if I replace the position with x plus lambda, then you get the same displacement at the position x. Right? That's essentially what this means. So let me erase some of the details in here. Sorry about that. I'm going to erase lots of the details in here. All right. So let's say it like this. So this is the position x, and we have the amplitude u in there, and that's the position x plus lambda. We should have the same amplitude in here, and the distance between these two positions is equal to lambda. Right, so therefore, when I increase x by lambda, somehow the argument of the cosine should increase by the period of the cosine. So we know that the cosine has this period, 2 pi, and so therefore somehow this k multiplier converts that displacement lambda to angular change 2 pi. So you can then think of it like this. I'm going to pass to the next page in here. So k multiplied with a displacement of the position by lambda is actually a change of angle by 2 pi radians. So therefore k is equal to 2 pi over lambda. Right. This is a quantity that we use a lot, so it has a special name. This is called wave number. Our space is one-dimensional, so we're talking about a wave in one-dimensional space. So in that case, we can describe this as a number. But in 3 dimensions, this can be considered as a vector. There's also a direction in there because you need to take the dot product with the position and things like that. But let's just forget about it. It's not that important in here. So I'm just going to describe this as a number. There's another thing in here. So I mean, that's just related with the wavelength like that. So we are going to remember at some point. So another thing, so the argument of the cosine was this: k times x minus k times vt. Of course, you can think of this as a function of time. So this is also periodic with periodic in time too. So that means in that case, if I increase the time by the period, I'm going to get the same thing. So what is it? So periodic in time, so capital T is the period. So that means, well, I can do it like this. There are 2 different ways of doing this. So k times v multiplied with the period, that's equal to 2 pi. You can actually think of it like that. This implies that this is the case. Or I can just think that, of course, this number is basically the angular frequency in here. So omega is the angular frequency. So that's equal to 2 pi divided by the period, if you remember. Because we have seen these sine omega t, cosine omega t arguments before, so you can easily remember that that's the case. So you can see that kv is equal to omega in here, so that's 2 pi over t, the period. So somehow this omega in here is called the, 2 pi over the period, that's called the angular frequency. Right? Why did we call this angular frequency? Because this is 2 pi times the frequency. So it's just a number which is proportional to frequency, but we just multiply it with 2 pi. Right? So therefore, instead of a wavelength, we use wave numbers. Instead of periods, we use basically angular frequencies. So most of the time in physics, when we are describing waves mathematically, this is what we do. How can I read the velocity? Velocity is basically, you can see that, where is it? It is that relationship in here. Velocity can therefore be written as omega divided by k. So because of this fact, I would like to write down the waveform in that form. That's also what the book does. Cosine of k times x minus omega t. Right, that's the waveform. But just keep in mind that since the cosine has the period of 2 pi, I can easily relate this with the period of the position and period of time. Right? This is basically what you should remember. So k times the period of position should be equal to 2 pi. Omega times the period in time should be equal to 2 pi radians. And so from here you can find both k and the omega in terms of the well-known physical properties of the waves. Right? You can just try to remember it like that. Why do I choose this k and omega form? Because this is simpler. It is easier. We don't have to write too many things inside. So just in that case, just remember that somehow we can relate them to the wavelength and the period like that if we want. And of course, there's also one more relationship, that the velocity is equal to omega divided by k. So in any case, in modern physics, for example, you are going to see all of these relations later. So that's actually called the phase velocity. There are other velocities of the waves as well. But it appears that at least for electromagnetic waves which are propagating in vacuum, it appears that there's just a single velocity and all velocities are the same. And so as a result, this formula holds true in there. So then let's pass to the electromagnetic waves. So electromagnetic waves are waves where the displacement, we don't have any displacement. We just have vacuum, we have space, empty space, and there are these electric and magnetic fields in there. So as a result, I'm just going to use blue color for expressing the electric fields. So as a result, there is this electric field property at each point in space. Okay, and somehow this should display this wave form in space. So as a result, they have shapes like that. So I'm just going to try to do this as perfectly as possible, but it's usually not possible. So as a result, at different points in space, we have different electric fields. And somehow if I don't know, look at the tips of these electric fields, the tips somehow provide this sinusoidal wave profile. Right? So this is one of the complicated things in here. So in the case of, for example, waves which are propagating on tight ropes, on strings, or on water, we can directly see the waveform because somehow we know that there is something there that is visible, something that we can touch, and so we immediately see the waveform in there. However, the electric field is not something like that. Usually when we draw the electric fields like that, of course, the tip has no position actually. We are essentially drawing a vector, which is a vector property defined right at that point in here. And how long I would draw this arrow for the electric field depends on my choice. For the same magnitude of the electric field, I could have drawn the arrow much more longer in there, for example. So as a result, this wave profile is not visible, and that's one of the difficulties in understanding these kind of waves. So essentially, we have this line in here. So for every point on that line, there's an electric field. I'm not going to draw it in here. So for every point, there's an electric field. And at every point, the electric field somehow depends on position, and it changes. And somehow, if you try to draw this electric field amplitude as a function of position in a separate graph paper, you are going to see a sine curve. But of course, the sine curve is not in the real space, right? So that's one of the difficulties in here. So another thing in here is that this electric field is perpendicular to the to this propagation direction. So there's a direction of propagation in here. So let me write it down like that. This is propagation direction. So the wave profile also will depend on this direction in here. So as a result, this is, I mean, if you go along the x direction, you see this sinusoidal change. So as a result, this is that, but the electric field will be in a perpendicular direction. So I'm going to call this as the y direction. All right, we are not done. There's also a magnetic field, because somehow we have said that the electric energy and the magnetic energy, somehow they are converted into each other. And that is how these waves somehow propagate in space. So as a result, there are also magnetic fields. So it appears that in this case, the magnetic field is also perpendicular to the x-axis. So I'm drawing waves with almost the same magnitude, but of course, just keep in mind that this is just a drawing. The electric field and the magnetic field does not have the same units. So as a result, they cannot have the same magnitude, right? Just keep this in mind. But somehow, if I draw the magnetic field, so let me also talk about the direction. So the magnetic field should be therefore in the z direction. And so somehow it appears that the magnitude of the magnetic field is proportional to the magnitude of the electric field. So therefore, at the point where the electric field has the maximum amplitude, we also have the magnetic field have the maximum amplitude. At a point where the electric field is 0, we also have the magnetic field being equal to 0, and so on. So we have 0 in here, magnetic field like that in here. So just again keep in mind that there are these regions in here. I'm going to use this one. In this region, for example, the electric field is along the positive y-axis and the magnetic field is along the positive z-axis. But in here, both directions are reversed. So the electric field is along minus y and magnetic field is along minus z. Okay. So there is this kind of a rule in here. Of course, we are not going to show these kind of things. So in a proper course of electromagnetism, you are going to derive these facts that the electric field is perpendicular to the propagation direction and it's perpendicular to magnetic field and so on. But let me just write this thing down in here. So the electric field within that or with that order, magnetic field and the velocity of the propagation forms a right-handed. I'm going to call this as frame, just like the XYZ axis. If you remember the discussion of the right-handed reference frames, XYZ axes, we call them right-handed if the cross product of the unit vector along x and the unit vector along y gives us the unit vector along z. We have to use the right-hand rule for this. So if we have, at least for the directions, not magnitudes, but at least for the directions, if these vectors in that order forms a right-handed frame, in that case we will call this as a right-handed frame. So that's one of the things that you may want to remember. So there's actually a very specific direction. Once you know the direction of the propagation and the direction of the electric field, you know the direction of the magnetic field. All right, so as a result, we have, therefore, I'm going to mathematically write down the wave profile. So for the electric field, first we have an amplitude. Okay, and then we have the cosine or sine function, I don't care which. The wave is propagating along the x direction, so therefore we have kx minus omega t. We're not finished. The electric field is a vector, so therefore this is along the y vector, so the y direction, sorry. Along the y direction, from here we get plus or minus signs, but that's basically along plus or minus y. So as a result, this is the wave profile, waveform of the electric field. What is the magnetic field? Since I don't have much space, I'm going to use this extra information in here. I don't need this. I use this fact to actually remember in which direction the magnetic field should be chosen. So magnetic field has a direction along the z direction, which can become minus z depending on the trigonometric factor. So the function is again cosine. Argument is again cosine minus omega t. There is no extra phase. Just keep this in mind. So as a result, for waves propagating on a rope, perhaps we have one displacement, or the waves in water, for example. But for electromagnetic waves, we talk about two different kinds of displacements in a way, where one is the electric field and the other one is the magnetic field. They are both transverse. Transverse means that the displacement of the displacement of the wave is perpendicular to the propagation direction. So transverse means this electric and the magnetic fields are both perpendicular to the velocity of the propagation, all right? Otherwise, we would call the wave as the longitudinal wave. All right, we are not done yet. There's another thing in here. So we just draw this x-axis only. That's somehow unfortunate. But of course, a wave cannot move along a line. So it's not possible to consider a wave that is present only on a line. The wave is present in a region, in a three-dimensional region. Just like the water waves cannot be present on a line, it is on a surface, right? These are waves on a surface. The electromagnetic waves are inside three-dimensional volumes. So as a result, what we have drawn in here are in three dimensions. So that's the confusing part. And a lot of people actually do not draw this because it's a lot of very confusing. So I'll try to draw it in here. So if you get confused, just forget about it because that's not that important. So when I, of course, writing down this wave profile in here for the electric field, I just show the x coordinate because somehow this implies that the electric field does not depend on the y coordinate of the position and the z coordinate of the position. So that means on this plane, for example, at every point the electric field should have the same amplitude. Okay, just that's what I'm going to draw in here. So I have just drawn the electric field right at that point, but it's the same electric field at this point, and also in here, and also in here, and so on. So also in here too, and in here too, and so on. So therefore, basically on this YZ plane, this is also called a wavefront or something like that. On this YZ plane, at every point, the electric field has the same magnitude, same direction. Similarly for the magnetic field. So magnetic field in here is like that, in here it is like that, and so on. So at every point, the magnetic field has the same magnitude and same direction. Okay. But of course, if I choose a different plane in here, I don't know what that plane might be, but still parallel to this YZ plane. So on that plane, of course, the electric field might have a different magnitude and different direction. For example, it might be along minus y instead of plus y. Might be smaller, so let me show a smaller vector in here, and so on. So at every point, of course, the electric field would be smaller. In any case, so as a result, when you see a picture like that, a lot of people draw this thing like as a picture like that. But just keep in mind that this is in three dimensions, so the real picture is a little bit more complicated. So we are going to use this fact. And moreover, the motion, so just keep in mind that this whole thing, together with these planes, plane profiles, they are moving along the propagation direction with a fixed velocity. As a result, this is one of the things that you should keep in mind. So since on a plane, the wave displacements, the electric field and the magnetic field has the same value, because of this, these are called plane waves. again, there is an unphysical assumption that these waves are extended to infinity in all directions, along the x direction, along minus x, or minus y plus y, or whatever, the z direction. So we are assuming that these this wave is present everywhere. This electric field is present everywhere. But of course, physically, this is nonsensical. So that means that since the electric field has both electric and magnetic field has some energy density, that would imply that the total energy of the universe is infinite. Total energy of the electromagnetic wave is infinite. So in reality, of course, the electromagnetic waves can never be plane waves. None of the waves can be actually these sinusoidal waves. They can only be pulses. But as I said, these are mathematically more convenient, so that's why we are working with them. Okay, so next what I'm going to do is I'm just going to use these expressions. I'm going to use this picture and these expressions, and I'm going to apply Maxwell's equations, all the equations that we have seen to these, and then show that, well, yeah, that actually conforms well with these equations. But we are going to see that, of course, the velocity should have a fixed value.